So in section 3.4, we're going to start talking about motion. And this is a topic that's going to come up frequently because it's just a really nice application of rates of change. So we first have to deal with some just vocabulary related to this. So we've talked about average rate of change, we've talked about instantaneous rate of change, and just kind of a summary of all of this. The average rate of change is always done over an interval of time. So it's never at one moment, it's over an interval of moments. Graphically, it's the slope of a secant, the slope between 2 points on a curve. And we think of it as delta x over delta t. If we are going to need to be dealing with average rates of change, it will specify using the word average. That will get complicated a little bit once we learn how to find the average values of functions. There's a slightly different meaning there, but when we get to average value of functions, we'll deal with that then. But if we're talking about an average rate of change, they will say average. Instantaneous is at a specific moment in time, and that's the slope of the tangent, the slope of the curve, the derivative, and is defined using our difference quotient here. If a rate of change is not specified as average, we assume it is instantaneous. They're not always going to say the word instantaneous, but if all they say is find the rate of change, it implies instantaneous for us. In terms of motion along a line, we have displacement, which is the change in position. So if we think of x as represents a position, delta x, the change in x, would be the displacement. It is commonly called S of t. There was actually a debate going on among calculus teachers online about why S of t, and basically they feel it comes from the Latin word situ, which means the site or place that something is. But for whatever reason, we are using S of t for displacement. We have average velocity, which is our displacement, change in x, over the change in time. That's the velocity you're used to finding, where you have 2 moments in time. Instantaneous velocity, or if we just said velocity, because instantaneous would be implied, is the instantaneous rate of change of displacement. Please note it's of displacement. And so it would be the derivative of our displacement. So dsdt in Leibniz notation or s prime of t in Newton's notation. But then we have to talk about speed. Speed is the magnitude of velocity. So we take away the direction. Well, if we're talking about motion on a line, the direction's positive or negative. So if we take that away, we're actually finding the absolute value of the velocity. And it doesn't matter whether it's average or instantaneous, it's done the same way. But if we're assuming, because it doesn't say average, that this is instantaneous speed, that means it's the absolute value of the derivative of displacement. If we continue along with that, acceleration is the rate of change of velocity. And again, we're assuming instantaneous because it doesn't say average acceleration. So instantaneous acceleration then is the derivative of velocity. So v prime of t in Newton's notation, dv dt in Leibniz notation. But since velocity is itself the derivative of displacement, that makes acceleration the derivative of displacement, or the second derivative of displacement. So our acceleration would be s double prime of t, or d squared s dt squared in Leibniz notation. Then, just because I like to throw this in, jerk is an actual term in motion. Jerk is the rate of change of acceleration. If you've been thinking about, if you've ever ridden a roller coaster and you've gotten off and said, wow, when we went around those turns, it was really jerking my head around. You were using the term jerk in the correct use, because you were talking about the rate of change of acceleration. That's what causes that motion, that feeling of jerkiness. So jerk, being the rate of change of acceleration, would be the first derivative of acceleration, a prime of t or dA dt. But because acceleration is the derivative of velocity, jerk's the second derivative of velocity, v double prime of t, or d squared v dt squared. But since velocity is the rate of change of displacement, jerk would be the third derivative of displacement, s triple prime of t, or d cubed s dt cubed. So please don't get me in trouble by calling your siblings third displacements or third derivatives of displacement and then blaming me, that's all on you. One thing I did want to talk about is when we talk motion, we talk a lot about things speeding up and slowing down. And it's a bit more complicated than you think because speed itself is not a super easy thing to calculate, especially when you move beyond linear motion. So it's nice to be able to talk about speeding up and slowing down without having to refer to speed itself. So when we talk about something speeding up, that means the velocity and acceleration are going in the same direction. It's like you're running along and somebody pushes you from behind to give you a boost. Whereas slowing down, velocity and acceleration have to have opposite directions. It's like you're running along and something has a rope and is trying to hold you from running. So the way we tell if something is speeding up or slowing down is we look at the signs of velocity and acceleration for that specific moment in time. If the signs are the same, in other words, both velocity and acceleration are both positive or they're both negative, then it's speeding up. If the signs are opposite, in other words, velocity is positive, acceleration is negative, or velocity is negative and acceleration is positive, then you would say it's slowing down. Some examples to help kind of go with this, I will go ahead and deal with in a separate video.